Okay, so now, okay, it's already over six. We can start now. So this is your penultimate week of your problem solving session for your NPTEL course. So I hope you have been enjoying this course. We have been like finding a grip on this course. We are almost reaching towards the end. So 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 there is one more week of this problem-solving discussion, and then probably we could also have one more session. So that additional session would be a conclusion session. So we will try to summarize things or try to discuss some specific issues. If you really, if people are having, then you can join this meeting and like try to clarify them in this uh, session because that is going to be right before your test. So I think that would be that session would tentatively be take place on 21st of March. So that is before your exam. So okay, but today we are going to discuss uh, Laplace transform and also delta function. So these are new topics again, which was introduced in the week 7 of your course. So we'll go through some of the specific problems that are vitally needed to understand various aspects of your uh, mathematical techniques. So that is what the uh, idea for this problem solving session. So this is your week 7 Laplace transform and delta function are your topics, and so the uh, so particularly we'll see what are Laplace transformations and what are its inverse Laplace transformations, and one specific application that we will look at, that is like using them we can solve ordinary differential equations. So ordinary differential equation which we have been discussing quite a lot. I think like maybe last 2 weeks we spent time on that, and then we'll talk about what are delta function. So so this problem solving session like aims uh, to to help you in solving assignments. So so uh, so in general, other than that, like if you have any other general query, you can always ask here. Mhm. Okay, so yeah. So before going to Laplace transform, so I would try to make you recall what were Fourier transforms were. So Fourier transforms, like I hope like you have gone through like at least once in this NPTEL course, uh, which was introduced during the discussion of Fourier series expansion. So in Fourier transform, like you saw, the definition was something like as you can see, if you are given some function f of t and you want to do you want to apply Fourier transform on this function, were achieved by this, which is given right here. The integral goes from minus infinity to infinity, and where you take the integral of your function f of t with exponential I omega t, that is minus I omega t. So when you do that, like you get a function only in domain variable omega. So that was your Fourier transform. So what happens now in Laplace transform? So like the Laplace transform is defined by this, which is given right here. So this integral is your definition for Laplace transform. So Laplace transform also you have here also you have a function f of t. Then you upon doing Laplace transform, you go to a different space or whose domain variable is s. So the difference usually comes the domain variable, like the domain variable in Laplace transform, which is this is s right now, so which is actually achieved by this exponential of uh, minus st. So this s is basically is a complex number. Earlier, when it was in the case of Fourier transform, you only had omega, which was just simply a number, or like uh, I mean that is just a real number. But now you have s is some complex number. So this s, which is appearing right here, that is s is some alpha plus I omega. So what happens, like introducing this kind of complex uh, uh, domain variable, it helps in certain like it helps to resolve specific problems. Like for example, like Fourier transform does not exist for functions f of t whose above integral does not converge. So what happens in certain Fourier transforms, like when you do this Fourier transform of f of t, this g of omega like will not converge. That means it would be something uh, infinity. Like so, for those cases, you cannot do Fourier transforms. Instead, what you can do, like you can apply Laplace transform on those kind of diverging functions. So, uh, mm, so here, this kind of Fourier transforms are diverging in nature. So you can like you can avoid this diverging behavior when you try to do this Laplace transform, because what happens where here in uh, the variable, which is domain variable, which I was talking here, which is alpha plus I omega. This alpha, what it does when you take basically minus st, so you basically have minus alpha t and minus I omega t. So this alpha t, basically what happens, this suppresses the increasing the suppresses the diverging nature of your functions when you try to do this Fourier transforms, because here you will not have this problem of divergence, because because your argument or that domain variable s is something alpha plus I omega, and when you do that, you get a factor of exponential of minus alpha t, which will basically actually suppress your uh, diverging nature. So that is the reason, like uh, we choose Laplace transform instead, like for particular cases when Fourier transforms doesn't work. So, and with besides it has other lot of applications and other uses. Like we also see some of those in today's discussion, and yeah, and there have been many other such discussions already in your course. Like you can, I hope you would have uh, like already seen them, or I would say, like if not, then just go through them. So those would be well explained in more breadth and more detail. So yeah, and so using this definition of Laplace transform, you can here you have some of those like some of standard results. So you can like you can also prove all these results from from this fundamental definition of Laplace transform. So that is nothing new here, but those are some standard results. Like people often try to remember them because they come very often, and when you remember some of these results, you can just directly apply and solve problems. So particularly, it helps really more when you deal with a problem, when you deal with a lot of problems. So it's better to remember them. But also, if you have curiosity to know like how this comes, like you can just simply like deduce all these results from this uh, definition right here. So, so yeah, Laplace function of one is Laplace transform of one is basically one over s. Then Laplace transform of uh, t to the power n, that is n factorial over s to the power n plus 1, then Laplace transform of cos at, that will give you s over s squared plus a squared, and so on, you can see. And some more other properties that I have given here. These are also very useful. Uh, so you can, so when you apply, these are some particular form of functions given here in this column one. So when you apply Laplace transform on all, so you can, uh, so that is basically a of Laplace function of f1 t plus b of Laplace function of f2 t. So you have this. So yeah, uh, so that is your first property. And second, when you apply Laplace function of f of at, then you can write this as 1 over of a g of s by a. So and so on. So these are also like, I believe like that is also well discussed by your uh, like by your, I mean, by the course instructor. So I hope you've like, again, like if you really want to know how these results are coming here, like you can check them. So and yeah, these are some more specific features that I hope you should try to see like how they are coming. Then moving on, so here also you have Laplace function of derivative of a function, Laplace transform of a derivative of function. That is also, you can do that, and its result will look something like this, and its double derivative and and integral and so on. So like moving on, like we can see like how this works here, how you can like use these properties and definitions of Laplace transform. Like we can all check them by solving some of the problems. Like first, like we can see like here just you need to calculate the Laplace transform of each of the given uh, for each of the functions which are given here. So let's see, like for the first one, the given function is your f of t is exponential of minus 2t sine 4t. So, um, so yeah. So first of all, like uh, these things, like you can start from the very beginning from your definition of like integral, like which I was showing up right here. So this is your foremost definition of Laplace transform, which all comes from here. So besides, if you know these properties, the following properties which are given here, these results right here, each of those results and these properties, if you can all together, like you can try to understand like how this like results can be used, then you can directly apply them in any questions and you can get the results. You can get answers for any given question, for any given Laplace transform of a function. So for any arbitrary function, you can easily calculate them by using these standard results. So so that is what like we will also see here. Like you can see uh, here you have one exponential function multiplied with one trigonometric function, that is sine function. So we have Laplace transform of a sine function right here. Like here you can see this is your Laplace transform of sine at will give you a over x squared plus a squared. So we can use that property in the question that we are trying to see right now. And also we have exponential. So exponential, that is this one, the one which is above it. So Laplace transform of exponential at will give you 1 over s minus a. So using both these, like we can see like how we can get that. So first of all, uh, Yeah. Mm. Or else like yeah, okay. Uh, Let me make this just to um, cos square or let it be that. Okay, fine. So yeah, exponential of minus 2t and this right here. So first of all, here you see exponential is multiplied with sine 40. So you can use this right here, the third one. So the third one tells you that if exponential of at is multiplied with your function f of t, then its Laplace transform will be something of the form g of s minus a. So here also we'll do something like that. So here you see exponential of minus 2t is multiplied with f of t. You can say your f of t is sine 40, or let me say uh, this is my some other. This is h of t. So my h of t is something of the form exponential of at f of t. So that is my property third. So when you take its Laplace transform, you get something g of s minus a. So when you take the Laplace transform of this, you get something g of s minus a. So that is here also you would get when you take h of t, when you do Laplace transform, so you will get something uh, g of s uh, s plus 2. So then this s plus 2, then what is then g of s plus 2? So uh, your so when you have f of t, when you do Laplace transform, you get g of s. But when you multiply e of at f of t, and when you do Laplace transform, you get g of s plus 2. So the same way, I think like your f of t was sine 4t. So when you do Laplace transform, you get the Laplace transform of sine 4t. So from this results, you can see you can use this result, Laplace transform of sine 80, that is a over s square plus a square, right there. So that will give you 4 over, because your a is 4 according to that formula. So according to that formula, you can say your a is 4. Then what was that? So that was a over s square plus a square. So that is a that is 4 over s square plus a square. Then again your a is 4, so that is 16. Then but that is not the your complete question, because your complete function was exponential of at multiplied with sine 40. So when you do that, what happens like so uh, so your minus 2t when multiplied with sine 40, then that will give you 4 over s plus 2 whole square plus 16. So because here, as I told you, this is your property right here. So you have to use that. So when exponential is multiplied, when exponential 8 is multiplied with your f of t, then whatever your Laplace transform earlier, just because of f of t, what you have to do there is when exponential is multiplied, just you change the argument from s to s minus a. So here, here since we had uh, a was equals to minus 2, like according to this property right here, the third one. So a is minus 3 minus 2. So what do you do? So when let me write this. So the property says when exponential of a t multiplied with f of t, that gives you g of s minus a. So here a was minus 2. So that's why when it was multiplied with sine 4t, and the whole of the Laplace transform of this whole will be whatever the Laplace transform that you got just because of sine 4t. Just in that expression, you have to replace s from s to s minus a. So earlier you have had s square plus 16. Now you will have, instead of s, you will have s minus a, that is s plus 2. So s plus 2 whole square plus 16. So that is your that will be your final result of this Laplace transform. So similarly, like you can check for the other one. So that is t, your f of t is t cube exponential of minus 3t. So similarly, again, we can use one of the property right above here. So yeah, so this one. So you can see the property number fourth. So property four, it tells that when uh, like when a like factor of t to the power n is multiplied with your f of t, then your final result would be something this. So again, we'll see. Let's say my let's say h of t is my function, or like whose Laplace transformation that I'm looking forward, uh, is given as t cube exponential minus 3t. So, uh, so I will say that my f of t is exponential of minus 3t. So here again, when I have a function f of t, when I take its Laplace transform, it gives g of s. Uh, Again, when I have a and when I multiply factor of t to the power n on this f of t, and when I take Laplace transform according to the property fourth, which I was showing up right here, so that will give you minus 1 to the power n and derivative of g of s. So so that is what you will end up when you uh, do the Laplace transform of this whole thing. So again, let's see here. So here, first you take the Laplace transform of f of t, that is exponential of minus 3t. So that will give you uh, so exponential of minus 3t. It's a Laplace transform again. You will check from the property right here. Uh, Here. So this is the result which you will get from Laplace of any exponential, that is 1 over s minus a. So just do the just write that result right here. That will give you 1 over of s plus 3, because since Laplace of EAT is actually 1 over of s minus a. So again, when you see then what happens? T cube is multiplied with this exponential of minus 3t. Then again, using this property, you can say when you do the Laplace transform, you will get minus 1 cube because here n is 3. Then dn. So our dsn. So g of s. So your g of s is this one. This is your g of s. So n is 3. So let me replace n with 3. So you have to take three derivatives of your g of s. So your g of s is, so that means, so your, so if I say that, um, um, yeah, so your Laplace transform of h of t, that is Laplace transform of t cube e minus 3t, will give you minus 1 cube is negative. Then you have to take three derivatives. So like just you have to take simply straight three derivatives. You will see that this whole thing will give you 6 over s plus 3 4. So that is what I've written here. So this one, just calculate the derivative and you will get. So okay. So I hope you are following. Is it fine, Nachiketa? Like, are you getting these things?
Yes, I understood.
Oh, okay. Okay, good. So, fine. So then, um, next one was, uh, like, it is some trigonometry function right over here. So we'll see what, how can you get for this kind of functions. So sine here t. So okay. So let me call this as h of t. So again, again in this question, you see you have, I can write this h of t if you more convenient way, as let's say I can 1 by 2a cube. Yeah, I mean this is nothing to simplify here. But I was telling like just at was 80. So writing separately, you can see that when you take Laplace transform of this h of t, so in the RHS also you will take the Laplace transform. It's 1 over 2a cube. So so 1a will be cancelled out from here. So you have 2a squared. So Laplace transform of t cos a t. So then from here you can just simply use the result of Laplace transform of sin a t, which is given up right here again. So Laplace transform of sin a t is a over s squared plus a squared, plus a squared, then minus of minus 1 over 2a squared, then Laplace transform of t cos a t. Again, here what you can do, first when you do the Laplace transform of cos a t, like this is again using the same property which we just did for this one, t cube exponential of minus 3t. So you have to use this result right here. So here n is 1 because we have only t is multiplied. If there would have been t cube or t square, then more other higher order derivatives would have been used. So if it would have been t square cos a t, then we would have been using d square over ds square. But now only t is multiplied. So so I can write this part minus 1 of 1, since n is 1, then d by ds, only single derivative of of g of s. So g of s. So g of s is the Laplace transform of only cos at. So so maybe I can show you. So let me write it here. Laplace transform of cos at is g of x. Laplace transform of cos at is -1 d by ds g of s. So so yeah, and I can use a over s squared plus a squared minus 1 over 2a squared. So this will be yeah, this will be plus, and d of ds, then you have s over s squared plus a squared, which is your g of s, that is your Laplace transform of cos at. So again, you can use the result from here, that is Laplace transform cos at is s over s squared plus a squared. So again, using that result right here, you have to just take a derivative, and then yeah, from here you can just simply solve it. Just you have to take the derivative and then you have to add both this term, and finally you will get 1 over s squared plus a squared whole square. So that is your uh, answer for this problem. Then yeah, then just like that we can check one more case, that is 1 minus let's say your h of t is 1 minus exponential of t by t. Let me see if that is negative of t. Okay, so yeah, again this one, so you can see, um, so again, like whenever a function is given to you, first like try to assess it, like what kind of function it is, like what is the exact form of this function, uh, from this table which I have shown here. So like the one which we are trying to solve, this 1 minus exponential of t by t. So you can see that like you can get from this one the part from here, f of t by t, because yeah, t is divided in the denominator. So only in this uh, property, like in only in this property, you can see that maybe you can get a result by using this property. So because the form here is matching with the one which is we are trying to solve. So we are trying to now solve one of one minus et, 1 minus exponential of t over t. So using this, you will see that you can able to get it. So it's Laplace transform of this usually gives integral of s to infinity g of u du. So use applying this, you would surely get. So again, so your h of t is given this one, and let me say that your f of t is 1 minus t. So Laplace transform of f of t by t gives you the Laplace transform of f of t over t gives you this one, s to infinity z of u du. Yeah, this is this one right here. So using the property, we can get it. First, what is this GU? So this GU is basically your Laplace transform of f of t. So first you have to determine this. So your f of t is 1 minus et. So that is Laplace transform of 1, then Laplace transform of exponential of t. So that means your g of u is, so Laplace transform of 1 is 1 over s, then Laplace transform exponential t is 1 over of s minus a. So again, using from the above results, you can write this. So Laplace transform of any general form of this kind of exponentials, you will have s minus a, and Laplace transform of 1 is 1 of s. It's basically the Laplace transform exponential of at. The one Laplace transform 1 is also the Laplace transform of exponential of at, where your a is basically 0. So that is about. So yeah, so you got your g of u, then you can just simply use your g of u to get the final Laplace transform. So I can just write here. So you have to integrate this s to infinity g of u du. So here this is what you have to evaluate. So s to infinity g of u is 1 over of sorry, let me write this in terms of u, like, because I this is u, this is u. So this is just basically uh, your Laplace transform variable, your new domain variable when you uh, after when you do your Laplace transform of 1 minus exponential t. So I'm just calling it to be u, because instead of s, why am I calling it to be u? Because you have to integrate it with respect to s. So you have to say that, like, you are in like you are taking some other dummy variable which you will integrate it, and after that integration will give you your final Laplace transform variable, that is your s. So that is just bit trivial. So nothing like intricate I'm trying to speak here. So your g of u is 1 of u minus 1 by u minus 1, and you integrate over s to infinity. So when you integrate this, then you will get you will get your final result in terms of s. So yeah. So when you will integrate, you will see the first term is basically your ln u, and your second term is ln u minus 1. After when you do the integration, then you have to evaluate it within its limits. Then that is basically you will see you will get um, that is ln u minus 1 s to infinity. So the first one you will see when you put infinity, that will go away. The first one will give you 0 from the so when you put ln, the I can write it as ln 1 minus 1 by u, and so yeah, so ln uh, yeah, when you put infinity, so let me say what I'm telling right here, when you put infinity first, so when you put your infinity in your ln u by u minus 1, so you can write that as 1 by 1 minus 1 by u. So when you put infinity right here, so that will give you basically 0. Like how that is, um, uh, that is u ln, 1 by infinity is 0, so that is 1 by 1 minus 0. So that is ln 1, and ln 1 is 0. So that is what your first term will contribute, that is basically 0. And your second term, so second term, like when you have to just substitute s in place of q, so then that will be ln s minus 1. So your final result is of t over t is ln s minus 1 s. So this is your final result. So okay, so these are some ways you can calculate Laplace transform of an arbitrary function. So using all these properties, you can eventually get the final Laplace transformations. So you need not to always start from the first principle, that is your definition of Laplace transform, where you have to again do this integral again and again. You have to go through. So it's always better to use these results and directly get your final Laplace transformations. So that is all you do. So like, so I hope this one is clear for you, Sugita.
Yes, it's clear.
Okay, so then one more case, like we can see where you can see that, like in certain places, like you get this kind of step functions. So usually, like it can be uh, like defined like some u of t minus a is 0. So this function takes 0 value when t is always less than a, and otherwise this function will take value 1 when t is always greater than or equal to a. So for those kind of functions, the Laplace transform is defined this way. So using this, like we can get one. So using this, like we can try to solve this one. So here it is given, like first we have to express this function in terms of unit step function. So the one using this u of t minus a function, and then evaluate its Laplace transform. So yeah, we can see here. So you can write your f of t um, as something like, let me see, right, t minus t, t minus 3. Yeah. So you have t minus 1. So when you have u of t minus 1 minus u of t minus 2. So um, basically what I mean here, like the way I define the step function right here, I can similarly write u of t minus a as something, let me say this is some uh, uh, yeah, this can be something g of t or h of t. um, so basically, so I have a something, see, uh, can I, yeah, so u of t minus a. Yeah, maybe I can simply tell you right here. So this one tells you like uh, let me write it completely, then I will tell you how this is t minus 2 minus u of t minus 3. So okay, so here you can see the first part. So your function is basically uh, t minus 1 when t is basically between 1 and 2. So that is like I can write, because u of t minus 1, this will uh, be this will be only equal to 1 if I have if my t is less than 1. That is from the definition of u of t minus a. So here again, so uh, if my value is less than 1, then this will give me 1. If my value is greater than, that is t less than 1, sorry, so this will give me 0 when t less than 1, and this here you will see that like I'm writing uh, uh, t minus 1 multiplied with u of t minus 1 and minus u of t minus 2. So for this term, this will give me 0 when t is less than 2, and this will give me 1 when t is greater than 1. So using this, like you can see, let's say that my t is less than 1. So my this is 2. So let's say that my t is uh, what I mean, my t is let's say something 1.5. So my t is 1.5. So then from u of t minus 1, it will be 1, because if my t is 1.5, u of t minus 1 will be 1, and u of t minus 2 will be 0, because my t is 1.5, so that is less than 2. So less than 2 will be 0. That is what this step function says. So so as a whole, for t equal to minus 1.5, when t minus 1 is multiplied with u of t minus 1 minus u of t minus 2, so this will be 0, and this is 1, so that is t minus 1. So this way you can write it. So when t is greater, now when t is something, let's say 2.5, u of t minus 1 will be 0. But you will see that u of t minus 2 will be 1. So no. So in this case, both will be 1, because here also t equal to 1 t equal to 2.5, like that is greater than 1, so that's why u of t minus 1 is 1. So and it is also greater than 2, so that's why u equal to t minus 2 is 1. So that is why t minus 1 is 1 minus 1, that is 0. So this way, like you can write this. Uh, so so the first term will only be so when I have t something between 1 and 2, I will always get this t minus 1, because I'm using this unit step function in this way. If it is less than 1, this will go to 0. If it is greater than 2, it will also go to 0. Like for one case which I have shown here, like I have taken t equal to 2.5, I have taken t equal to 1.5. Let's say if I take t equal to 0.5, there also you will see that uh, this the first term t minus 1 will go to 0, like that will be 0 minus 0 is 0. So this way, like it ensures that when I write my unit step function in this way, it says that it only gives non-zero. So I can write this as um, only non-zero when t is between 1 and 2. So that is how you can write. So 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 keeping this idea in mind, you can move on and we can calculate the Laplace transform. So yeah, so as I wrote here, so from here I can write t minus 1 u of t minus 1. The same way, like you can also comment for this. So this will be only non-zero when your t is only non-zero when t is your between 2 and 3. Again, you can do this similar analysis just like how I did here. It will you will see that your this will go to 0 when your t is less than 2 and also when t is greater than 3. So only when t lies between 2 and 3, this will be basically 1 and uh, or it is non-zero. Then you can only have contribution from this. So that is very useful when you use this kind of step functions. So yeah, t minus 1 t minus 2 is 3 minus t minus 2 plus t minus 3 t minus 3. So then I'm just multiplied the t minus 1 with the first vector, the 3 minus 2 with the second one. Then using the Laplace transform property, you can write, or let me also like write this in this way because I have t minus 1 from here. Like you just can just simply simplify it a bit. You'll get um, this is t minus 3. So yeah, t minus u of t minus 2, I take a common up here, and that will be 2 times of, yeah, 2t minus 4. So right. So I've just taken a common factor of u of t minus 2 from the second and third term, and so from there you get the expression. And yeah, from here you can just write, so using the property of Laplace transformation. So let me see if I've given you this. So there is one more property. So I'm writing here Laplace transform of f of t minus a t minus a is exponential of minus as g of s. Yeah. So using that here, I will get, first I have to take Laplace transform of u of uh, t minus a, t minus a, that is u of t minus 1. So that will give me exponential of minus s, and no, so that is, let's say that that's Laplace transform of something u of t minus 1, that is, let me write u of minus s, Laplace transform of t is 2 2s, Laplace transform of t is 3s, transform of t. So yeah, so this is what I can write from this property right here. So this is similar thing which I have also shown at the beginning. I think that would be there in the Laplace inverse Laplace transform. But yeah, so using this property you can write. So then your Laplace transform of f of t will be minus s by uh, this will be s minus 2 e minus 2s by s square plus e minus 3s by s square. So that from here like you will get this that is the Laplace transform. Uh, when you so the idea is like you first have to express this t minus 1 and 3 minus t with I mean your f of t function in terms of u of t's step function. So that is what I've done right here, and then you take the Laplace transform, and so that Laplace transform will basically give you this. So yeah, so that is what basically you can represent. Oh, like wait a minute. Oh, I'm sorry. I just written uh, this. This won't be just because. So like what I did right from this step. So after this line from here, so I'm using this property which I showed you right here. This one right here. So f of t minus a or multiplied with u of t minus a, it's Laplace transform of exponential of minus a is g of s. And at the same time, I'm also writing, I'm using this property, Laplace transform of u of t minus a exponential of minus as by s. So, so what I can write here, so this will be g of uh, u t minus 1. Similarly, this will be u of t minus 1. Let me check. Mm, so, Laplace transform of t minus a, t minus a is basically, yeah, this is Laplace transform of g of t minus 2, g of u t minus 3. So then your g of u t minus a, you can calculate it from this right here. So that is exponential of minus at, that is exponential of minus s by s. So this is exponential of minus s by s. So I hope so. This one clear for Nachiketa?
Wonderful.
Uh, Fine.
Yes.
Okay. Good. So then yeah, we can move on. So then your uh, next part is on about inverse Laplace transform. So in inverse Laplace transformation, so uh, so like after when you do this Laplace transformation, so that is basically where you go from your t domain, your variable t domain to your variable s domain. So you then um, when again if you wish to uh, go back to your previous domain from where you actually started your transformation. So in that case, like you can apply this Laplace transformation back again, but using the idea of inverse Laplace transformation. So using inverse transformation, you can go back to your previous like variable domain. So that is if you started with Laplace transformation from f of t to f of s, then then Laplace transform of f of t is basically your f of s. So but when you go from if you want to go from f of s back to the f of t, this one right here from f of s to f of t. So you use inverse Laplace transformation. So here you denote with L inverse of f of s will give you f of t. So you will see that like previously the results which I wrote down for there, those results like you can see right here. Yeah, if you just apply L inverse on those results, you will get back to the one which you were making your transformation. Like initially I was doing Laplace transform of uh, one, which was giving me one of s. Now when you do this, like when you apply Laplace transform on both sides, so that is Laplace transform of one and Laplace inverse Laplace one over s. So that is one is your result when which you will get when you do Laplace inverse Laplace transform on one of s. So yeah, so this is what you get when you do inverse Laplace. So same way, like you can get again those results. So which you did for Laplace transformations, like now just you want to do the uh, inverse Laplace transform on them, and you can get back your uh, initial results which you were started with. So that is how you will get for all these cases. And so similarly, we can see some questions right here. So um, so yeah. Um, so the first one is on so let me see. S is 2s minus 5 over 9s squared minus 25. So when you take Laplace inverse of f of s, so that is Laplace inverse of 2s by 9s squared minus 25 minus Laplace transform of 5 over 9s squared minus 25. So that will give you Laplace transform. So I can maybe write this in a appropriate way, that is taking 9 factor of 9 outside, and that will give p squared transform. So inverse Laplace transform. So again inverse Laplace transform. And here also I can do the same thing. I can take a common factor of 9 outside, and that will give me s square minus 5 by 3 squared. Yeah. So why I'm doing this, like why I'm trying to get this kind of form, because that is what my results are like. Because I'm seeing right here, I have like yeah, here you can see I have forms like s over s square plus a square, 1 over of s square plus a square, and s of s over s square minus a square. So I'm trying to get so in the denominator, since I'm having s square lying around here, so I'm trying to write something in a form of s square plus a square or s square minus a square. So that is why I'm trying to like achieve the those kind of form right here, and I finally already got some sort of structure like that. And you can see the first one, the first term right here, it is something of s over of s square minus a square. So s over of s square minus a square, you can see here from this one, I can write that this can be something related to with cos hyperbole. Then I have to check what is a here. So a, you will see that your a is 5 by 3. So I can write this as since I have additional factor of 2, I will add 2. Then also in the denominator I have 9. So 2 by 9 is your factor that is multiplied with cos hyperbolic of 5 by 3t. So 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 inverse Laplace transform of s over s square minus 5 by 3 whole square will give you cos hyperbolic 5 by 3 t. So that is the first one. And same way, you will see that in this case, you will also you can write this as 1 over of 3 sine hyper. This will be not hyperbolic, since let me check. This will be um, 1 of s square minus a square. So yeah, again, this will be also your hyperbolic, sine hyperbolic of 5 by 3 t. So yeah, so this will be your result. Then similarly, you can do for the second one. So the second one, like you have s- 1 of square plus a square over square. So in this case, like what you can do, uh, first again you have to try something. You have to try to get something of this kind of form: a square minus a square or a square plus a square. So how you can do that here? So this is bit little tricky, but you can do this. Let's say I am dividing and multiplying s on numerator and the denominator. Then I can write this as minus 1 over 2s. Then d of ds, uh, so that is derivative s square plus a square. So you can see like I can write this way. So why am I writing this way? Because again I have to make something of s square plus a square in the denominator or s square minus a square in the denominator. Since I have s square plus a square in the denominator, so it would be something of the form s square plus a square. But again, there is a square on a whole square on it. So like you will see that when I take a derivative, I can get that whole square thing. So I can write this as Laplace transform of 1 over s square plus a square. Basically, give me 1 over 2s square plus a square. So that is minus 1 over 2s. You see that derivative is done on of 1 of s square plus a square. Derivative means multiplying t to the Laplace transform of 1 of inverse Laplace transform of 1 of s square plus a square. So again, like I can like so I, for so what I'm doing, so I'm using the property which I showed you initially. So like here I have forgot to write. So here you can see. So in this case, uh, when we were doing Laplace transform t to the power n of f of t, like we were getting something of derivative. So using this property, we can get that. So what you do, since we are now doing an inverse Laplace, so multiply. So I mean, you do inverse Laplace, L inverse on both the sides. So you will get L inverse of uh, so when you do so using that property, I can say that when I do L inverse of En dsn g of s, then I would get uh, something t to the power n f of t. So something of this kind of structure. So using that, like I can write. So so the I was writing not here. So the same with that idea. So I can write minus. So this will be your single derivative is there. So that will be a single t will be there. Then your f of t. So f of t is basically so your f of t is basically your inverse Laplace of g of s. So the inverse Laplace of g of s. So when you do inverse Laplace transform of 1 over of s square plus a square, that will give you 1 by a sine at. So that is your Laplace transform, inverse Laplace transformation of 1 over s square plus a square. So then you can see that finally you can write my 1 over of 2as, or basically 1 of 2a 1 of s t sine a t. and and here you will see that again, you see that it is still not complete yet, because you have 1 over of s, because when you do the Laplace transformation, you when you do inverse Laplace transformation, you go from s variable to t variable. But here you see, here you still have s, so that means your that the Laplace transform is yet to complete. So that means you have to use the another property, that is 1 over of s. Uh, so this one over of s g of s is integral of 0 to t f of u du. So using that, I can write 0 to t t sine a t, or else to avoid confusion, let me say that I let me write this as some u for now. Yeah. So that is u, uh, u and u is u. So du. So this is u. Okay. Then so you just have to do this integral, and you will see that when you do this integral, you get something of this. So that will be your result. So yeah. So like I can like maybe I hope like you, if like you can give a try for the number third bit right here. So again, you just have to use the properties and you can get it. So so I hope like this one is clear for you.
Yes, it's clear.
Clear?
Yes.
Okay, so fine. So we can move on. So then this is one of the important place where Laplace transform actually helps uh, like helps us to uh, solve ordinary differential equations. So how you can do that. So you see that like you can we were discussing ordinary differential equations so far till last week. So one of the case like where Laplace transform can be used uh, uh, like uh, to get its solutions. So how that is actually done? So that is basically done in three steps, which I am showing up right here. So the first one is like when you have a uh, when you have this when you have this differential equation, you take the Laplace transform of the differential equation. So calculate Laplace transform. So take the Laplace transform of the differential equation, and then you express that after taking that Laplace transform of the differential equation, then you express it as some algebraic equation. Then solve this algebraic equation. Solve this algebraic equation. Then after when you solve, you again have to take the inverse Laplace transform of that final equation, the final solution of that algebraic equation. So you take inverse Laplace transform of it, and then you will have the final solution of your ODE. So we'll see how that is done. Before that, there are some again properties of or some results that you need. So when you take Laplace transform of uh, d of f by df by dt, that is SGS minus f of 0. So again, when you take Laplace transform of d square f by dt square, that is s square gs minus sfg f of 0 minus f prime 0. So yeah, so that is how it is written here. So these are again some results which I hope that would be uh, like uh, taught well by your course instructor. So I hope like if not even or if you are curious about these results, again you can check from those lectures which are already there on your NPTEL portal. So we'll see like how like one way like this can be solved. Uh, mm, so okay. Um, So yeah, so here one differential equation which I have taken here that is dy by dt ay equals to uh, e to the power minus bt. So its initial condition is given at y of 0 is this is certainly some linear differential equation of. So we used to apply the idea which we were doing earlier. So instead of doing that, like how we can see like Laplace transform can help us to solve this differential equation. So you can see that first you have to take the Laplace transform of this differential equation. So so when you take Laplace transform, so the first Laplace transform of dy by dt plus Laplace transform of y, then Laplace transform of to the power minus pt. So Laplace transform of dy by dt again I can use from here this result s of gs minus f of g. So that I can write it as uh, s of uh, uh, y of s minus y of 0. So what is y of s which I am writing here? So that uh, so when so y of t, when you do Laplace transformation, let's say that like this will be something of y of s. So that is what this y of s is. So I'm just basically using the this f of result right here, and then s of g of s minus f of 0. Similarly, I have also written here s of y of s minus y of 0. So plus a times Laplace transform of y, that is a times y of s. So Laplace transform of y of t is basically y of s, which I'm denoting right here. Then you have to take on the RHS as well, the same Laplace transform. So the Laplace transform exponential of minus bt will be 1 of s plus b, since that is what I showed you earlier as well. Laplace transform of exponential of at something always. Yes. So yeah, then from here you can see I can solve this. This is some sort of algebraic equation. So you solve this equation, s plus a equals to 1 over s plus b. So that is basically, so from here I can write I of s is basically 1 over of s plus a and s plus b. And again you have to take or maybe like I can just simplify this a bit. This s plus b minus s plus a over s plus a multiplied by s plus b. So why I'm doing this, like multiplied by, so I have so whole multiplied by 1 over b minus a. So what I did here actually, in this y of s, I multiplied and divided b minus a. Uh, like I multiplied b minus a on the numerator and divided b minus a on the numerator, and further on the numerator, I uh, added uh, added s and also subtracted s. So that is s minus s. So that will go away, and you will leave left behind with b minus a on the top. So on the denominator as well, we have a b minus a factor. So both will cancel and give you the same y of s. So I just hasn't I didn't really um, make any bigger change right here. I am just rewriting it because you will see that in doing so, I can simplify my y of s as 1 by s plus a minus 1 by s plus b. Because you have to do, like, simply I am using the partial fraction technique. So you apply that and you will get this, because in doing that only you can take the inverse Laplace transform. So when you do inverse Laplace transform here, so take inverse Laplace transform, that is basically you will get y of t. So that is give you y of t. So 1 of b minus a, and when you take inverse Laplace of 1 over s plus a, that will give you exponential of a t minus exponential of minus b. So yeah, this is what the final result will be. And so yeah, then uh, okay, then again you can try for the I think, yeah, I have one more question right here. Same, you can see here as well. Mm, uh, you can do the same technique right here. First, you take Laplace transform of your differential equation. So the differential equation given here is t. So take Laplace transform on both the sides. So after when you take Laplace transform, so here Laplace transform of d square y of dt square will be something uh, using from here. Um, Let me write here Laplace of y square, Laplace transform of phi of t, then minus s of y s y of 0, then minus y prime 0. So I have just used that property as I was showing up right here. So that is the Laplace transform of your double derivative. So like this is some general property which you can always use it for uh, differential equation when you try to solve differential equations using Laplace transform. So in general, for nth derivative, this formula will be applied. So yeah, so using that, or I can write s square as y of s. So Laplace transform of y of t is y of s. I'm writing that is bigger case y uh, as a function of s. Then so yeah, Laplace transform of t square y, Laplace function of y, Laplace function of t. Then here I can write the results. So y of s uh, square y of s is y 0 is y prime of 0. So then minus Laplace transform of y is bigger ys. Then Laplace transform of t is 1 over of s square. So this I am writing from the property of Laplace transform of t to the power n is basically it gives n factorial by n plus 1. So yeah, so again you solve this algebraic equation, you will get y of s taking common from s square and 1, that is s square minus 1. And then I have, so you this this is actually equals to 1, and also this is equals to 1, which is given in your question right here. So the initial conditions are given y of 0 and y prime 0 are both 1. So using them here, so I have s plus 1, and that is equals to 1 of s square. So now you basically have to uh, write what is y of s from here. So your y of s is basically 1. I can write this as s plus 1 minus plus of 1 s square. That is 1 of s minus 1 plus 1 of s square minus 1. So and again further you can see right here uh, uh, the first term, like I can write some, when I like here from here you basically have to take inverse Laplace transform. So inverse Laplace transform, you can see like first term usually you can see you can get its inverse Laplace transform, that which will come out to be exponential of t e to power t. But again in the second term, so you have to get something in the denominator of s square plus a square or s square minus a square. So here you say it is something in the product of s square times s square minus 1. So again, you will apply the partial fraction technique, which I just did earlier for the previous question. So I can write this y of s again, s minus 1 plus when you apply the partial fraction technique, you can write this as s square. So this total term right here, the second term. I can write it as this way: 1 over of s square minus 1 minus 1 over of s square. So then again, like you, yeah, from that is your final form of y of s. So that is how you get the final form of an algebraic equation. Then from here, you again you have to take one more. uh, So from here, the third step, the final step is to take inverse Laplace transform of the algebraic equation that you obtained here. So when you take inverse Laplace, so inverse Laplace of y of s, then inverse Laplace of 1 s minus 1 plus inverse Laplace of 1 of s square minus 1, inverse Laplace of 1 of s square. So this is minus. So so that will give you. So this is your y of t inverse Laplace of bigger y s is y of t. Then the transform of 1 over inverse Laplace of 1 over s minus 1 is uh, simply exponential t. Then this is your inverse Laplace transform of 1 over s square minus 1. That is basically your sine hyperbolic. You can check the properties that I have given earlier. And this is your inverse Laplace of 1 over s square, that is t. So that is your final form of your uh, solution. So that is your final solution for your differential equation, which uh, which was given right here. So this is how like Laplace transforms can be very useful in solving various ordinary differential equations, and these are really used in some particular cases so extensively, like there are things like called like electrical circuit systems. So in those cases, you can really see them like they are well used. So like this one, so this part is clear for you.
Yes, it's clear.
Yeah, okay. So like, do you have any other doubts? Like maybe not just this one, or even like previously also what we have discussed over the past weeks, or maybe now itself with any problems or any kind of questions with the course, or else everything is fine for you. No,
No, no doubt.
no doubt. Okay, so fine then. So that is good. So then we can. So that is how Laplace transformations are all about. So now we'll look into some one more new topic. So that is your delta functions. So yeah, so delta functions, or rather, they are technically the distributions. So like delta functions, like I hope again that is well cleared or well explained uh, in your NPTEL lecture sessions. So I hope you would have already accessed from your portal. Like those lectures are already out. And so what delta functions are basically, like these are uh, some distributions. Like if you have some random, let's say, like for example, like in physics, you come across various discrete distributions, like yeah, a charge distribution, a discrete charge distribution, or discrete point mass distributions, or even yeah, point mass distributions or charge distributions. Like you see them like those distributions. Generally, you can express them, or uh, you can like show the form of the distribution using delta functions. So delta function again are really very vital, and they are so vital. You will see that like they will comment again and again in various places, just like the one which I just told you right now, like it is like for discrete distributions, like we saw, we use this delta functions for in certain cases, like we use conservation laws, like where delta function will again come into picture. So it is very important to know what are delta functions and their properties, and then their uses particularly. So, and again, you will see that like how delta functions like can be used, or what I mean, some of the important mathematical features or these delta functions, like I have shown you right here. So using them, like you can solve like some problems involving like distributions, which really you have to express in only in terms of delta functions. Uh, so delta function, like it is defined. Um, so delta of x minus a uh, either 0 or infinity. So it can be only 0. So when your x is not equal to a, so that is basically a. So this is a. So when your x is not equal to a, so you have 0, and x equals to a, so you have some infinity, so or some non-zero. It's not it's not always have to be infinity, but some large value. So it's like a very sharp peak at the point a. So let's say if I have some coordinate system right here. Uh, so so let's say x equals to a is this is the point. So right in this point, I will have a sharp peak. Uh, say that. So this is just simply a sharp peak you will get at point x equals to a. So that is the function. So that is just a like a distribution rather. So like if you have many such delta functions, so this is for f of x equals to delta of x minus a. So if you have delta x minus a plus delta x plus a, then you will have a peak on x equal to a, and also you will have a peak on x equals to minus a for if you have delta x plus a. So that is how like you can write delta functions. And so when you integrate this delta function, like let's say from limit from this to this, so this is some a minus epsilon to a plus epsilon limit, you will get 1. So that is the normalization of delta function. So that is uh, uh, yeah. So that is the um, one of the foremost feature of delta function. Then then some other properties following this delta functions. So using which you can easily deal with delta functions that is coming in various places. Uh, um, so when you write uh, so uh, so when you solve this kind of functions, you will see that like people also often call it as like test functions. So like when you multiply a function with the delta function and you take its integral, you just write that the value of that function will be that or the value of integral will be equal to the value of function at where the peak of delta function is. So the peak of delta function here is at x equals to a. So the value of this integral will be the value of function which you are multiplying with the delta function, that is f of x. So value of function f of x at x equals to a. So that is this is x equals to a. So so that is how you write your your integral when you have this kind of delta functions appearing. And one more thing you have to note it. So this limit that you are seeing right here. So basically, I'm writing. the integral of f of x delta x minus a dx is basically f of a when your limit lies outside of your of this delta function peak. What I mean, which I was showing right here, let's say if I my delta function is at x equals to a. So this is the plot for delta x minus a, and suppose I'm integrating this delta function with a function f of x from limits a to b. So if my limits lie in this way, so a is the point which is less than x equals to a, and b is the point which is greater than x equals to a, then only I can have a non-zero value of this integral. If my limits were outside, let's say my limits were, let's say this is the limit from this is a and this is b, then in that case I will have zero. So in that case there will be no contribution of this integral. So that is the important uh, point in this part of the or in this feature of this delta function integrals. So and again, if you have a derivative of delta function, then when you take then again you take the integral by multiplying a function f of x, then you have this result minus f prime a. So when you have the nth derivative of the delta function, this is your nth derivative, then you will have this result. So this is nth derivative of your function at x equals to a. And when you have delta function of k times x minus a, so you can write it as 1 over mod k, 1 over mod k delta x minus a. So when you have delta function of x square minus a square, you can express it as delta x plus a and x minus a in this way. So yeah, so using this like uh, features and definitions, we can solve some of the integrals right here. So the first one, so yeah, so in this question, so you have to integrate this delta function x squared plus 3x minus 10 to x plus 1. So I have to first uh, express this. Let's say that in this argument, this is g of x. I have to express this g of x something of the form x minus a x plus b or something of this structure, because that is how I can use this property. You can see that it has to do with last three properties, or rather particularly last two properties. So um, so how I can do that? First, you take the root of this function g of x. So like I can write g of x. Uh, so to take the root of this function, so I can just simply um, make it to 0. So this will be x squared plus 3x minus 10 equals to 0. So my roots will be, you can see that I can write this as plus of 5x minus 2x minus 10 equals to 0. So this is x equals to minus 5, and let me say this is x1 equals to minus 5 and x2 equals to 2. So these are two roots. So then I can write this as g of x as x minus or x plus 5 and x minus 2. So then how you can write, so when you so can write my delta function as x plus 5 and x minus 2. Then you have to use this property, right one, this one right here. So first you have to get this kind of form. So you can get this kind of form using you have to basically obtain the roots, or basically you will see that when you write this kind of factorized form. So first target is to get your factorized form when the argument of delta function something is of this way. So get the factorized form. So the factorized form is x plus 5 multiplied with x minus 2. Then I can write this as uh, and then after when you get the factorized form, then you use this property, the last property right here. So that will here a and b are basically your roots. So I can use them. Uh, so before that, I uh, yeah, okay. So then after when I got this property, I can write this as the integral multiplied with 2x plus 1. So this is my f of x, let's say. So, uh, so again, from the above property, you see that the first prefactor is 1 over mod of a minus b. So in this case, I have um, of a minus b, that is 1 over 5 minus of minus 5 of minus 2 mod, then delta of x minus a. Or what I'm writing here, like basically, just let me write this integral letter. Can write this as, so using that above property, I can write this as 1 over of 7, because here I have to write 1 over of a minus b. So here my a and b are, so these are my a and b, x1 and x2. So so when I do a minus b, that is minus 5 minus 2, that's minus 7, its mode is 1 over 7. And then I can write this as delta of x plus 5 plus delta of x minus 2. So just I have used this property right here, the last one. And then after that, you just basically have to use the integral. So minus infinity to delta. So 1 over 7 equals to delta of x plus 5, 2x plus 1, then dx, then again plus 1 over 7, delta x minus 2, 2x plus 1 dx. So my f of x is this function. It's my f of x, and here 2. So then again from your first property for delta function, you can write this f of x delta x minus a is your f of x. So my delta function peak for the first term of this integral is at x equal to minus 5. So at x equal to minus 5, so the minus 5 delta function peak is that delta function peak. So I have to use that as f of minus 5. So f of minus 5 is 1 over of 7 f of minus 5. So the value of this integral is f of minus 5 minus 5. So that is minus 5 2 multiplied with 1. Then the same here, you can write 1 over of 7 delta function peak is at minus 2. So this is x equals to my x equals to 2. So that is 2 times of 2 plus 1. So this will basically give you uh yeah. So this is minus 9 over 7 plus 5 by 7. So I think I might have mistaken some sign. So the thing is like which I was writing right here, um, g mod of x minus 1 g prime. So actually there will be a negative sign right here, which like I will tell you how this negative sign was actually coming. So this is actually 14 by 7 equals to 2. So that the thing is like if, when you write this property earlier as I was writing, so delta x plus 5 and x minus 2, that you write in this way: 1 over of uh, g prime x1 delta x minus x1 plus 1 over g prime x2 uh, yeah, delta x minus x2. So I say this is my x1 and x2. So this is the property so which I have used in this part. So using that, so you will see that g prime x1 will give you minus 7 and g prime x2 will give you 7. So that's why I was getting minus 7 right here and 7 here. So then basically you have to use that property like this property minus infinity to infinity f of x delta of x minus a is basically f of a. So that is what I did. So just like subtlety is there in the negative sign. Otherwise, it is all straightforward property. Then your second question was on so that is integral 0 to 2 x cube delta. So double derivative of delta function whose peak is at 1. So this one again you can use the property. So you can use the second property right here. So this one right here. So we have three derivatives. So that will the result will be minus 1 to the power 3. That is negative. And negative that is minus 1 to the power 3. F of you have to take three derivatives of a function f. Your f of x is cube. You have to take three derivatives of x cube, and then you have to get its value at 1 because your peak is at 1. Peak is at supposed to 1. So then your negative 1 multiplied with triple derivative of f of x, that is that you will get. So when you take first derivative, then you will get 3x squared. When you take not triple derivative, actually here you have two derivatives. So sorry. So first when you take first derivative, you get 3x squared, and you take one more derivative, it will be 6x. So 6x, but you have to take value of x equals to 1. So that is 6. So this will give you minus 6. So so the value of second integral will be minus 6. And third, like third you have integral of 0 to pi by 2 sine x sine square x delta x minus pi. So this one you will see that like the value will be 0 because you see that peak is at x equals to pi, but your limits is at 0 and pi by 2. So that is like your this is 0 and this is pi by 2 and this is pi. So your delta function is on this point. So but when you're trying to integrate this sine square x with a delta function from 0 to pi by 2, so from this one, but in this limit you don't have any function of delta, so effectively this value of integral will be 0. So that is how you do. So like so this delta function part is clear for you, okay?
Yes, it's clear.
Okay, fine. So then good it is. So like we have completed this discussion as well on delta functions and Laplace transform. So then we will have one more week to discuss some other important topics. So like that will be your last session of this problem solving uh, uh, like the time that we are spending problem solving meetings. Then probably one more session that will be the concluding session, and then it is all over for your NPTEL course which you have registered. So yeah. So then I think we are already with our time, so that so we can maybe end our today's session right here. We can meet next time on next week uh, at the same time. So that is for today. So we'll meet again next time. Okay. So goodbye. So if you have any questions or anything, then you can ask, or otherwise we can end right here.
Thank you.
Okay, you do not have anything. So okay. So then okay, let's see. Uh, so goodbye. So we'll meet again.